Dear students, now continuation of the videos on set theory. In this video, I explain how to prove that n cross n is countable. N cross n is countable. See, to understand the concept in this video, this is the continuation of some previous videos. I have started countable sets in the previous video. And if you go through that video, then only you can understand this one. Because what is definition of countable set, denumerable set, and how to prove that a set is denumerable or countable, that I have explained already in the previous video. So you have to refer that video also. Now in previous video also I have proved n cross n is countable. But to prove that n cross n is countable, there are several methods. I explain today one more method which is seems to be more simple, and then the choice is left to you. In the previous video, I have proved that n cross n is countable using this concept. What is that? If A is countable or A is denumerable, and f from A to B is injection, that is 1 1. Injection 1 1. Injection means function is 1 1. Then f of A is countable or denumerable. Using this concept, I have proved that n cross n is countable. But today I use different concept to prove that this n cross n is countable. You know what is n cross n? First I explain what is A cross B. How to define A cross B? A cross B is set of all order pair AB such that A belongs to A, B belongs to B. This you have already studied. Cross product of two sets. Here, first A belongs to first coordinate. This is called first coordinate. B is called second coordinate. This is A cross B. Now, what is n? N is set of natural numbers 1, 2, 3, 4, 5, and so on. This is n. Now, therefore, I write n cross n here. N cross n is equal to 1 1, 1 2, 1 3. 1 4, 1 5, and so on. Next I take 2 1, 2 1, 2 2, 2 3, 2 4, 2 5, and so on. Next 3 1, 3 2, 3 3, 3 4, 3 5, and so on. There are infinitely many elements. It extends infinitely along row. Along column also it extends infinitely. Because next is I take 4 1, 4 2, 4 3, 4 4, 4 5. Next it extends like this. Next 5 1, 5 2, 5 3, 5 4, 5 5. And here it extends indefinitely. Infinite elements are there. Here also it extends infinitely. Now I use this concept here. When you say that set is countable means if it is possible to write the elements of this set in a sequential order, then we say that set is countable. Repeat once again. If we express the elements of a set in some definite order, sequential order, if we find out a rule to write the elements of a set in some order, then we say that set is denumerable. Now what are the elements of n cross n? Infinite elements are there. But I explained how we can express the elements of this set n cross n in some sequential order, and then I conclude that it is denumerable. For that, say I consider this one. Sum of the coordinates. 1 means 1 is first coordinate, 1 is second coordinate. Here sum of the coordinates is 1 1. First I write this one. Next I take sum of the coordinates is 3. Next I go to 1 2. What is one more element having coordinate 3? 1 2 2 1. Say 1 1. I show this order of the elements in the arrow mark. 1 1. Next I take 1 2. Next to 2 1. Next after 2 1 I go to downward 3 1 because sum of the coordinates is 4. 3 1 2 2 1 3. All these three are ordered pairs having sum 4. 3 1 2 2 1 3. Next I go to this 1 4. What is the sum of the coordinates here? 5. One more is 2 3. This is also sum is 5. Next to 3 2. Sum is 5. Next 4 1. Sum is 5. Then I come to downward here. 5 1. Here up to this, these are having sum of the coordinates 5. Next is 5 1. What is the sum? 6. Next element is having sum of the coordinates 6 is 4 2. Next is 3 3. Next is 2 4. Next is 1 5. What are these elements? They have the sum of the coordinates 6. Next sum of the coordinates 7. What is this? 2 5, 3 4, 4 3 and 5 2. These are the elements having coordinates. Sum of the coordinates 7. Now I write the elements of the set n cross n. Therefore, in this order, what is the first element? 1 1. Next is 1 2. Next is 2 1. After 2 1, next is 3 1. Next is 2 2. Next is 1 3. What is the next element? Next after 1 3 we have 1 4. Then downwards 2 3, 3 2 and 4 1. After 4 1, sum of the coordinates 6. 5 1, 4 2, 5 1, 4 2, 3 3, 2 4 and 1 5 and like this. Now this is the order in which we can write the elements of the set. That means we can arrange the elements of the set in this sequential order. This is the order in which we can arrange the elements of the set n cross n. Therefore, this n cross n is countable. See, this is one more method. Here we have used directly this. If the elements of the set are expressed in the form of in a sequential order, then it is countable. So n cross n is countable. Prove that the unit interval 0 1 is not countable or uncountable. Now we prove this by contradiction. Contradiction means first we suppose that 0 1 is countable. Countable means since it is infinite, it is denumerable. We have to prove that it is denumerable. But we prove that these elements of that set 0 1 cannot be arranged in any order. If we arrange elements of 0 1 in some order, then the arrangement not includes all the elements between 0 and 1. Therefore, it is not countable. That is the procedure. Now, the elements of proof I explain like this. The elements of 0 1 can be expressed as point A1, A2, A3, etc. non-terminating decimal representation, because greater than 0, less than 1. In between 0 and 1, elements are always of the form point A1, A2, A3, etc. where this each AI is greater than or equal to 0, less than or equal to 9. Each ai lies between 0 and 9. Now, if possible, let 0, 1 is countable. So it is our assumption, but we get some contradiction for this. If possible, let 0, 1 is countable. Then the 0, 1, the set 0, 1 can be written as x1, x2, x3, x4 and so on. We can enumerate elements of 0, 1 like this. What is x1? x1 is point, I write x1 as point a11, a12, a13, a14, so on. x2 is point a21, a22, a23, a24 and so on. x3 is point a31, a32, a33, a34 and so on. See, we have assumed that 0, 1 is countable and the elements of 0, 1 are like this. What is each aij? Aij is aij greater than or equal to 0, greater than or equal to 0, less than or equal to 9. Now this is our assumption. The set 0, 1 is countable and we have elements of 0, 1 are only like this. Now what we prove is there exists element y which is equal to point b1, b2, b3 and so on. Point b1, b2, b3 so on, bn and so on. Which belongs to 0, 1, which belongs to 0, 1 and not equal to any of x1, x2, x3 and so on. See, what we prove is, next thing is, there we can find out another element y which lies between 0 and 1 but which is not equal to any one of this x1, x2, x3, x4. Then what happens? Our assumption is wrong. 0, 1 consists of only this element is wrong. Therefore, it is not countable. Now we have to prove this. What do we have to prove? We have to prove that there exists element y which is not equal to any one of this x1, x2, x3 and so on. For that, we define that b1, b2 etc. like this. bn is equal to 1 when an n is not equal to 1 and it is 2 when an n is not equal to equal to 1. This is the important thing now. We have defined y as point b1, b2, b3 etc. b1. It is in between 0 and 1 and to prove that y is not equal to any one of x1, x2, x3, we have taken bn as 1, an is not equal to 1 and 2 when an is equal to 1. Now this, what happens now? This y differs x1 by first position. What is the meaning of this? That means this bn is not equal to an for all n. This is the important thing. Therefore, if we define bn like this, then bn is not equal to an for all n. Because in first place, we have n is 1. Correct? Take n is 1. Then a11 equal to bn is 1 if an is not equal to 1. Then what happens? b1 that y differs by x1 in the first position, this position. Second, What is this? X2, y is not equal to x2. Why y is not equal to x2? Because they consider this. X2 is point A21, A22, etc. We have taken like this. Now see here, if A22 is not equal to 1, then this B2 is equal to 1. So y differs by x2 in this position, y differs by x3 in this position. Finally, y differs by xn in this position, a and n. So y is not equal to any one of these x1, x2, x3. Now, what does this implies? y escapes from our enumeration. That means we have enumerated the elements of 0, 1 as x1, x2, x3, etc., xn. But there exists one more element of this 0, 1 which is y and not equal to any one of this x1, x2, x3, etc., xn. This, what does this indicate? Our assumption is wrong. Elements of 0, 1 cannot be expressed in the any order. So 0, 1 is not countable. Now this result is important because we prove two important theorems now. First is the set of real numbers is not countable. Set of the real numbers R is not countable. So far we have proved that set of rationals is countable, n cross n is countable, and some results of countable sets. That is subset of countable set is countable, and what is that? Union of two countable sets is countable, and so on. Now this is the important theorem. The set of real numbers is not countable. To prove this, we make use of this previous result. What is that? 0, 1 is uncountable. Now, suppose proof of this. Suppose set of reals is countable. Now we have proved in the earlier videos. I explained that one. Every subset of countable set is countable. Did you understand this one? For that you have to refer previous videos. I cannot explain once again this one. Every subset of countable set is countable. I have already explained that one. You refer that proof. What do you have to do now? Set of real numbers is not countable. Suppose again we assume that R is countable. Then every subset of countable set is countable. This 0, 1 is subset of R. But just to have proved that 0, 1 is not countable. Therefore, this contradicts that every subset of a countable set is countable. Hence, R is not countable. So the set of real numbers is not countable. Next is set of what do you want to prove? Rationals is countable. We have proved that set of rationals is countable. Prove that set of all, let us take this as theorem. Set of all irrational numbers is not countable. Set of irrational numbers is not countable. This is the next theorem. For that again we use contradiction method here. To prove this, see we have already proved that set of rationals is countable. You have to refer the video, that one. Set of rationals is countable. Now suppose that set of irrationals, I write this as Q dash notation, is countable. Is countable. It is our assumption. Since the set of rational numbers is countable, rational numbers is countable. This we have already proved. Set of rational numbers is countable. Union of two countable sets is countable. We have proved this also. Here Q dash is irrational, set of irrationals. We have assumed that this is countable. Set of rational numbers is countable. This we have already proved. What is set of rationals and irrationals? R. Since union of two countable sets is countable, R is countable. R is countable. But just to have proved that R is not countable. R is not countable. So, if we assume that Q dash is countable, it contradicts the fact that R is countable. But this R is not countable. Hence, Q dash is not countable. These are some results on this set theory. So, in all these videos, there are I think 15 videos. In all these 15 videos, from first video, I have started with definition of set. What is definition of set? Then, what is relation? And different types of relations. And then, what is partition of a set? And one fundamental theorem of partition of a set. Then next is De Morgan's laws, generalized De Morgan's laws. After that, I have discussed countable sets. I think all of you followed that videos. If you followed these concepts, what I explained in the videos, you appreciate that my effort, and I do some more videos on next number theory and groups and so on. You go through that videos, and if you like my these videos, don't forget to give like. Yes, thank you.